Here's the best part, don't you agree, where we actually try solving some real world type problems. In other words, word problems using these equations. We're going to solve problems that will translate into factorable expressions equal to 0. What does that mean? If they're factorable, we're going to have a product, and if it's equal to 0, we're going to be able to use the ever popular zip product property. So let's go ahead and do it. We know the 3 steps. First of all, understand what the problem is. That takes a reading usually and a second reading. Develop and carry out a plan. This usually involves setting up some equations or a single equation. Then you find the answer. And don't forget this. Does it make sense? Always ask yourself that question. We do a quick review here using equations that are factorable. Let's see. There is no common monomial, so we skip right by that step. And we look to see, we have a quadratic trinomial, which will usually factor into, if it will factor at all, into 2 linear, I call them linear because they are to the first power, linear binomials. I call them binomials because they have 2 terms in them. Let's see, what will we use? I know they're both going to have to be negative, right? If this is negative and this is positive, the only way that could happen is these are both negative. Now, 2 factors of positive 18 that when we add them together will give us negative 18. Trying to think what that could possibly be. So we can't use negative 1 and negative 18. No, because if we add those together, you get negative 19. So what else could I do? What other factors are there? Well, I could say negative 3 and, let's see, negative 6. But if I add those together, I'm going to get negative 9. How about negative 2 and negative 9? I add those together. Oh boy, this one is prime. Prime, that means that it cannot be factored. So with this one, we would not be able to apply the zero product property because we can't develop a product. There are other ways to solve this. We could use the quadratic formula to solve this. We'll get back to that another time. Let's look at this one. Oh, I'm liking this one. We do have a common monomial we can take out of this. And now I have my product and my zero. I can apply the zero product property. For x equals 0 and x minus 1 equals 0. You get your product and then you take each of the factors and set them equal to 0. So I have x is equal to 0 or x is equal to 1 from this one. How about this one? Ooh, this one looks really good. This is a perfect square. The square root of this would be x. And this is a perfect square. The square root of this would be 10. And if I say 10 times x and double it, I get 20. So here is a case of a perfect square trinomial, which will always factor into a binomial squared, which we have here, right? So I've got my mini equation from one factor and my mini equation from my other factor. I know, they're identical. So x is equal to 10. And I also would have 10 here. That would be referred to as a redundant solution. When the factors both give the same answer, you have a redundant solution. X is equal to 10. Let's try solving a word problem. The square of a number equals twice the number minus 10. So equals, that's good. We're going to have a nice equation here. And let's say n equals our number that we're interested in. So we define our variable and we say n squared equals twice the number minus 1. Now there is another way you could interpret this, isn't there? Twice the number minus 1. I'm thinking that this is saying twice the number and then minus 1. So I'm interested in using the zero product property because I've got a quadratic. Anytime you see that you have a quadratic, consider the zero product property, which means I need to get a 0 over onto this side. So I'm going to subtract 2n from both sides. That will 0 this term. And I'm going to add 1, and that will 0 this term. So now I have the 0. I still don't have the product. What do I need to do to get the product? This is a perfect square, and this is a perfect square. So I'm thinking this is probably a perfect square trinomial, and I'll know in a moment. 1n plus 1n is 2n, and my sign in my binomial is this. So what's my number? My number is 1. The square of 1 equals twice 1, which is 2, minus 1. Perfect. It makes sense. A square region. All right, I'm just going to start right off drawing. I know it doesn't look like a square, but it is. A square region with an area of 1 square unit is cut from a square piece of cardboard. Okay, so I'm going to change colors here. A square region, I don't know how big the square is, but this square region with an area of 1 square unit. So I know this is 1 by 1, right? That would be an area equal to 1 square unit. It's cut from a square piece of cardboard. The remaining cardboard has an area equal to 3 square units. So the area that remains is equal to 3. I better mark this one as area large, equal to 3 square units. What is the length of a side of the large square? Well, this area here plus this area is equal to 4, right? This area plus this. So the area of the large square is 4. And since the side length also equals the area, I can say the s squared equals 4. I'll take the square root of both sides. S equals 2. Does this seem reasonable? If this is 2 times 2, before I cut anything out of it, it's equal to 4. When I cut one square unit out, then I'll have the 3. Yes, it does make sense. See you back in class.